Welcome to the final chapter of the course, where we'll discuss SVMs in more detail. In this first part of the video, we'll discuss what support vectors are and why they matter. In the last chapter we talked about logistic regression, which is a linear classifier learned with the logistic loss function. Linear SVMs are also linear classifiers, but they use the hinge loss instead. The standard definition of an SVM also includes L2 regularization. Remember these diagrams from chapter 2. The logistic and hinge losses look fairly similar. A key difference is in the flat part of the hinge loss, which occurs when the raw model output is greater than 1, meaning you predicted an example correctly beyond some margin of error. If a training example falls in this zero loss region, it doesn't contribute to the fit. If I remove that example, nothing would change. This is a key property of SVMs. Support vectors are defined as examples that are not in the flat part of the loss diagram. In the figure, support vectors are shown with yellow circles around them. Another way of defining support vectors is that they include incorrectly classified examples, as well as correctly classified examples that are close to the boundary. If you're wondering how close is considered close enough, this is controlled by the regularization strength. Support vectors are the examples that matter to your fit. If an example is not a support vector, removing it has no effect on the model, because its loss was already zero. Even though we use the name support vectors, it's really the non-support vectors that are remarkable. Comparing with logistic regression, there is no flat part of the loss there, and therefore all data points matter to the fit. Critical to the popularity of SVMs is that kernel SVMs, coming later in this chapter, are surprisingly fast to fit and predict. Part of the speed comes from clever algorithms whose running time only scales with the number of support vectors, rather than the total number of training examples. Although it's not the perspective we've taken in this course, you may encounter the idea that SVMs maximize the margin. I want to briefly mention this viewpoint for completeness. The diagram shows an SVM fit on a linearly separable dataset. As you can see, the learned boundary falls just halfway between the two classes. This is an appealing property. In the absence of other information, this boundary makes more sense than a boundary that is much closer to one class than the other. The yellow lines show the distances from the support vectors to the boundary. The length of the yellow lines, which is the same for all three cases, is called the margin. If the regularization strength is not too large, SVMs maximize the margin of linearly separable datasets. Unfortunately, most datasets are not linearly separable. In other words, we don't typically expect a training accuracy of 100%. While these max margin ideas can be extended to non-separable data, we won't pursue that avenue here. You can think of this as another view on what we've already defined SVMs to be, which is the hinge loss with L2 regularization. As it turns out, they are mathematically equivalent. In this part of the video we'll see how to fit nonlinear boundaries using linear classifiers. Consider this 2D toy dataset. The two classes are not linearly separable. In other words, there's no linear boundary that perfectly classifies all the points. If you try fitting a linear SVM on these points, you might get back something that predicts blue everywhere. However, notice that the red points are all close to the point, 0, 0, in the coordinate system. Let's create two new features, one of which is feature 1 squared and the other of which is feature 2 squared. That means values near 0 will become small values, and values far from 0, both positive and negative, will become large. What happens now if we plot the points? Well, now they are linearly separable in this transformed universe, because all the red points are near the lower left and all the blue points are above and to the right. We can fit a linear SVM using these new features and the result is a perfect classification. But then we might ask ourselves, what does this linear boundary look like back in the original space? In other words, if we took these axes and unsquared them, what would happen to the shape of the boundary? In this case, we get an ellipse. So, what's the take-home message here? It's that fitting a linear model in a transformed space corresponds to fitting a nonlinear model in the original space. Nice. In general, the transformation isn't always going to be squaring and the boundary isn't always going to be an ellipse. In fact, the new space often has a different number of dimensions from the original space. But this is the basic idea. Kernels and kernel SVMs implement feature transformations in a computationally efficient way. Let's look at some code. We'll need to use scikit-learn's SVC class, rather than linear SVC, to allow for different kernels. The default behavior is what's called an RBF or radial basis function kernel. Although it's not computed this way, you can think of this as an extremely complicated transformation of the features, followed by fitting a linear boundary in that new space, just like we saw for the simpler squaring transformation. While many nonlinear kernels exist, in this course we'll focus on the RBF. With kernel SVMs, we can call fit and predict in all the usual ways. Let's look at a decision boundary. This is definitely not linear, and, as a result, we've gotten a higher training accuracy than we could have with a linear boundary. We can control the shape of the boundary using the hyperparameters. As usual, we have the C hyperparameter that controls regularization. The RBF kernel also introduces a new hyperparameter, gamma, which controls the smoothness of the boundary. By decreasing gamma, we can make the boundary smoother. The second image shows the same data set with gamma set to 0.01. The boundary looks smoother. The third image shows gamma equals 2. Now we've reached 100% training accuracy by creating a little island of blue around each blue training example. In fact, with the right hyperparameters, RBF SVMs are capable of perfectly separating almost any dataset. So, why not always use the largest value of gamma and get the highest possible training accuracy? You guessed it, overfitting. In this part of the video we'll compare our two linear classifiers, logistic regression and SVMs. Let's summarize the points we've covered throughout the course. Both logistic regression and SVM are linear classifiers. Both can be used with kernels, but this is more common with SVMs because the predictions are much faster when the number of support vectors is small. While both can be coerced to output probabilities, this is much more natural with logistic regression. Both can be extended to multi-class with a 1 versus rest scheme or by directly modifying the loss. In logistic regression, like most methods, all data points affect the fit. SVMs have the special property that only a subset of the examples are support vectors and the rest can be removed without affecting the fit. While the term logistic regression doesn't refer to a particular type of regularization, the term SVM typically refers to a linear classifier that uses the hinge loss and L2 regularization. Let's compare the use of our two methods in scikit-learn. Logistic regression is imported via sklearn.linear_model.logistic-regression. And what are its key hyperparameters? The first is C, which controls the amount of regularization. Smaller c means more regularization and vice versa. The next is the type of regularization. Scikit-learn supports L2 and L1. We also discussed methods for extending a binary classifier to multi-class. This hyperparameter will probably affect your results less than the previous two. There are a bunch more hyperparameters that scikit-learn exposes, but these are the ones I consider the most fundamental. Don't be afraid to read about the rest. As for SVMs, they can be instantiated from sklearn.svm using either linear SVC for a linear SVM or SVC for a kernel SVM. You can actually also fit linear SVMs via the SVC class by setting the kernel to linear, but you may find linear SVC to be faster. The key hyperparameters of the SVC class are C, just like with logistic regression. The type of kernel, we only talked about linear and RBF, but scikit-learn supports a couple others. And gamma, which only applies to the RBF kernel and controls the smoothness. Smaller values of gamma lead to smoother, or simpler, decision boundaries, and larger values of gamma lead to more complex boundaries. As with logistic regression, there are certainly more hyperparameters and I encourage you to check them out. Finally, I want to direct your attention to scikit-learn's SGD classifier. SGD stands for stochastic gradient descent. Although we didn't cover SGD in this course, it's worth knowing about SGD classifier, since it can handle very large datasets much better than the other methods we've discussed. We've been talking about how logistic regression and SVM are just two types of linear classifiers, and SGD classifier really brings this point home. In fact, to switch between logistic regression and a linear SVM, one only has to set the loss hyperparameter of the SGD classifier. It's just like we said, the model is the same, and only the loss changes. SGD classifier works pretty much like the other scikit-learn methods we've seen. One gotcha with SGD classifier is that the regularization hyperparameter is called alpha instead of C, and bigger alpha means more regularization. Basically, alpha is the inverse of C. Congratulations on completing the course. I hope you enjoyed it. Please feel free to ask any questions in the comments section. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. Congratulations again. See you in the next video.